In this video, we're going to learn about linear and angular velocity. There's two different velocities that we have. They are related, which we'll see in a little bit. And we're going to learn about how to handle these in different problems in this class. So first off, linear velocity. So let's imagine we have a car, and I know my car is pretty poor drawing here. But let's say it's traveling in a direction and it travels 100 miles in 2 hours. Well, in that case, we're going to say its average speed, or in this class velocity, we're going to use them interchangeably. Speed and velocity are not truly the exact same thing, but as I said, we're not going to worry about the differences right now. It would be 100 miles in 2 hours, or simplified 50 mph for miles per hour. And in general, if you want to find the linear velocity, you take the distance that you traveled, divide by the time that you traveled for, and d over t is equal to v. That's your linear velocity. So it's talking about distance you traveled divided by the time it took you to do that. That is linear velocity. Now, technically, you can travel in a straight line, you can travel in a curved line. It's still going to be the distance you traveled divided by time. This next one, angular velocity, is not going to be traveling a straight line. It's only talking about something rotating. So the terminology we use here is uniform circular motion. And in this case, that means you have some sort of object that's traveling around and round and round a circle. It's rotating here. And if we want to talk about how fast it's rotating, we will usually use angular velocity. Now, just in case you're not aware, this little symbol right here, this is the lowercase omega. That is a symbol we usually use for angular velocity. If you wanted to use W instead, not a big deal whatsoever, but just in case you're reading along and you see that written down somewhere, that's just a special Greek letter that we use for angular velocity. Now, if you want to talk about angular velocity, it's how fast you're rotating, and we're doing that in terms of the angle. And so the idea here is if we rotate, say, 300 degrees, sorry, let me make this look better here, 300 degrees in 2 minutes, then my omega would be 300 degrees divided by 2 minutes, or 150 degrees per minute. So angular velocity is talking about rotation. Now, I did that in terms of degrees, but we're not usually going to want to do that. We usually are going to prefer things in radians when talking about angular velocity, just like we were seeing in the arc length and area of a sector formulas. So yes, you can talk about angular velocity in terms of degrees per minute or degrees per second or things like this, but normally you want to talk about it in terms of radians, and the general formula is the theta is the angle you traveled divided by t. So compare these two formulas here. V, the linear distance, is d divided by t. D is the distance traveled, t is the time. Omega is theta divided by t, where theta is the angle we traveled divided by t. And this is how we find our linear velocity and our angular velocity. One more time, I want to remind you that the linear velocity, you can be traveling in a straight line, and that's fine for linear velocity, or you can be traveling on a curve. You can even travel in a circle, and you can still talk about the linear velocity. Imagine taking a car and just driving in a circle over and over again, maybe in a parking lot going crazy. That still could be talked about as linear velocity. That's what you would see on your speedometer there. However, we can only talk about angular velocity when we are rotating in a circle. So one of these, the angular velocity is a more restrictive idea compared to linear velocity. However, if we do restrict ourselves to the situation where we are traveling around a circle here, and we want to figure out what's the relationship between linear velocity and angular velocity, well, let's compare that if we move just part of this distance, maybe it's the whole distance, maybe not, then we have an arc length, we have theta, we have r, and we know from relationships, as long as we are using radians here, s equals r times theta. Or in general, if I want to say this s is the distance we're traveling, the actual distance here, then I can say it's d equals r theta. And now I'm going to say theta is the total angle we traveled, d is the total distance we traveled. And now if we see this, we can go ahead and divide both sides by t. And this would give us d over t is r times theta over t. D over t is the linear velocity. Theta over t is the angular velocity. And so now we know that v is equal to r times omega. That is our relationship between linear velocity and angular velocity. Okay, so let's see what we can do now to solve a problem. We're going to do a spinning wheel problem, and we're going to say we have a car. So a car is driving, and let's just say 60 miles per hour. The wheel on the car has a radius of 2 feet. Now, generally cars would not have a wheel that's radius 2 feet, but I'm just trying to make my numbers work out a little nicer here. What I want to do is I want to say find the angular velocity of the wheel in radians per hour. Okay, so what we have here is 60 miles per hour. That is my velocity, 60 mph. So we got one thing in our formula up here. We're trying to find omega, so we need to put in our radius here. Now we do need to be careful. This 60 is miles per hour. My radius is 2 feet. Those are not the same units. I need to convert them. I need to either have all feet or all miles, otherwise things are not going to work out. I'm going to choose to convert the miles into feet, and I happen to know, and if you don't know you can look it up, that there are 5,280 feet in 1 mile. And if I go ahead and multiply 60 times 5,280, I'm going to get 316,800. So 316,800, and this is going to be feet per hour. That's my linear velocity v, and we know v is r times omega. So 316,800 feet per hour equals the radius they told us was 2 feet times omega. We go ahead and divide both sides by the 2 feet. And what we're going to get here is omega, the angular speed, is 158,400 radians per hour. Now they didn't ask us to do this, but if I wanted to convert this to radians per second, here's how I would do that. And a lot of times we talk about like rotations per second with cars and things like that. So more often with like cars and things, they would do per second here. And here's how I would do it. I would say In 1 hour, there are 3,600 seconds. Again, if you don't know off the top of your head, you can work that out or look it up. And if we divide here, turns out my angular frequency would be 44 radians per second. Okay, so these are the formulas we have here in order to work out spinning wheel problems.